In the last class, we were looking at the second part of the theorem, how to convert a PDA to a CFG. So we started with an example, like if you have a language where each string has equal number of zeros and ones, then how do you build a PDA for that? So this grammar I just gave you just for reference. You should imagine we don't know this grammar. We need to derive the grammar. Okay. So this grammar is only for reference. We don't know the grammar. That's what you need to assume. We first build the PDA for the language, and then we need to convert that PDA to a grammar. Okay. Once we convert the PDA to grammar, then you need to compare it with this to see whether the grammar we got is correct or not. Okay, that's the idea. So sometimes we may know the grammar beforehand, or sometimes we may know the PDA beforehand. So we may need to, it is easier to reach the grammar through PDA sometimes. Other times it is easier to reach the PDA through grammar sometimes. Okay, in this case, both are easy. But sometimes we will know only the PDA. Okay, so imagine you don't know the grammar yet. We are building only the PDA. I'm getting constant noise from that side. So we discussed the algorithm of PDA here. Two of you got out? I mean, I just cannot imagine. Just now I said, I know you both are speaking. And again, you started chit-chatting. Get out immediately. Quickly. So we discussed the algorithm last time. If I have to recognize a language with equal number of zeros and ones, where each string has equal number of zeros and ones, basically 4 cases. If your next input symbol is 1, sorry, if the input symbol is 0 and the top of the stack is 1, then pop 1. If the input symbol is 0 and the top of the stack is not 1, then push this 0. So not 1 may cover multiple cases, that the top of the stack may be 0, or it may be $, or it may be empty stack. All these cases will be covered in not 1 case. Similarly, if the next input symbol is 1 and the top of the stack is 0, pop it. If the next input symbol is 1 and the top of the stack is not 0, push this 1. Okay. So basically, if it is opposite symbol, you pop it. Otherwise, push it. That's the same. That's the simple logic behind this PDA. Okay. And then, so we took one example, 0001111, and like these are the steps in which the stack is modified according to the PDA. So you see a 0, you push it. Again, you see next 0, push it. One more 0, push it. Now you see a 1, pop the top 0. Now you see one more 1, pop the top 0. Now you see one more 1, pop the top 0. That's it. So the stack is growing as you're seeing zeros, and it is reducing as you're seeing ones. Okay. And then what I mentioned is that basically on reading this entire string 0001111, the stack is coming back to the same state from where it started. Initially it started empty. Now after reading this entire string 0001111, it is coming back to the same state, that is empty state. Okay, so one can think that, or one so the rule is that the string which takes the stack from point A to similar point A, I mean, you can name the target point with a different name, but the state of the stack is exactly same. It is empty here, it is empty here, or there is one star or 1 0 here, there is 1 0 here, there are 2 zeros here, there are 2 zeros here. In between you are reading a string. Okay, so if you are starting from state, from some state of the stack, you are reading some string, you are going back to the same state of the stack. Then this particular string, which is taking the stack back to the same state, this string is said to be accepted by that portion of the PDA. Okay, so if 0001111 is taking the stack from empty state to empty state, then the 0001111 will be accepted by the PDA. If 0011 is taking the stack from one state to the same state, this 0011 will be accepted by this portion of the PDA. Okay, so you can think the entire portion of the PDA is accepting some string, some sub portion of PDA is accepting some string, and so on. Now you can convert it into the reverse from a different angle, from the grammar perspective. So whichever portion is taking the stack from, say, empty stack to again empty stack, that string can be generated by the start variable of the grammar. Okay. Similarly, this portion is taking the stack, say, from a single 0 back to single 0. In this case, it is 0 which is on top of the stack. These are symbols which you are reading. But on stack, when you read a 0, you pushed a 0 onto the stack. Now, in this step, you have 1 0 left on the stack. Okay. So you are popping that 0 at the end. So at this position, the stack is having a single 0. Again, at this position, the stack is having a single 0. Okay. So this string is taking the stack from single 0 state again back to single 0 state. So this string will be accepted or can be generated by a sub variable. So how do I say sub variable? Suppose if we take this grammar, now suppose I want to generate string 0011, then you can say, okay, this S goes to 0s1, again this S goes to 0s1, and then this S goes to epsilon. Okay, so now how you can think is this particular S. So let me just number them slightly differently for you to understand. So say this is S1, this is S2. So S1 is generating the entire string 0011. Okay, whereas S2 is generating only 01. This S2 has only 01 under it, whereas S1 has 0011 under it. Okay, so this entire string is being generated by S1, and only the inside 01 is being generated by S2. Technically, they are not really different S, like the other grammar we saw. Here, S1 and S2 are different, but this is not of that type. This S1, S2, they are same. I'm just telling you the difference like this. So this 0011 is being generated by the top S. This 01 is being generated by the second S. That's what I want to say. So this entire portion will be generated by the start variable of the grammar. Whatever is accepted by the entire PDA, that entire thing will be generated by the start variable of the grammar. Whatever is accepted by a sub portion of the PDA, that portion will be generated by a secondary variable in the grammar, smaller variable in the grammar, and so on. So that is the reverse way of understanding it. Okay. So this APQ, you have point P to point Q. You can name this entire portion as APQ, and this APQ, because we know the grammar independently, we just built the grammar independently. I'm just comparing it with that grammar. This APQ that we have here is equivalent to the S1 in this grammar. This will be APQ. Okay, and this will be ARS, the inner portion. This portion, this 0011 portion, from R you are going to S. Okay, so this will be ARS. So ARS is like the inner S in the grammar. Now what is the relation between outer S and inner S? S1 goes to 0, S to 1. Same relation will be there between APQ and ARS. APQ goes to 0, ARS 1. Okay, so what I'm saying is, after reading this 0, the stack goes to some state. And then after reading some portion of the string, the stack comes back to the same state. And then after reading 1, the stack again becomes empty. Okay, so now this can be converted to, this is basically a recursive kind of a thing. Like particularly when you have S in the LHS and RHS, that is like a recursive thing. Here it does not seem recursive because APQ and ARS may seem different, but if you think relatively, this APQ is greater than ARS, but this ARS is greater than ATU. So here ARS will be relatively APQ and their ATU is ARS. Okay, so you can, I am right now comparing APQ and ARS with S1 and S2 just for your understanding, but technically they are the same. You will understand once we look at the next example. So here we looked at a string of one kind, 0 power n, 1 power n. But we also need to look at the string of another kind. Zero zero one one 1100. Now this is not of the form 0 power n, 1 power n, but this is also a valid string in this language because this also has equal number of zeros and equal number of ones. Okay. Now for this, we will consider this other grammar example that we took. S goes to S1, S2, or SS or epsilon, and S1 goes to 0, S1, 1, or epsilon. S2 goes to 1, S2, 0, or epsilon. Okay, both grammars are same, but this is more easy to map with this particular example. So first, I start with empty stack. I'll just have $. Okay, now I'll not put all these markers where the redated is pointing. I'll just quickly show it. So first, you are reading a 0. How will you modify the stack? You push 0 onto the stack. You are reading one more 0. What do? Push 0. Now you are reading a 1. What should you do? Pop the top 0. You are reading one more 1. What do? Pop the 0. Now you are reading one more 1. What do? Push this 1. You are reading one more 1. Push that 1 also. You are reading a 0. What do? Pop this 1. You are reading one more 0. What do? Pop this 1. Okay. So now let's try to plot it. So here we have height going only up to 2. So initially its height is 0. Its height is 1. Its height is 2. Again it's reducing to 1, reducing to 0. Now again the height is increasing to 1, increasing to 2, reduced to 1, reduced to 0. Okay. So now this is not similar to the previous case. In the previous case, initially the stack is empty, again only at the end the stack is empty. But here, initially the stack is empty, in between also it became empty, again it rose, again it became empty. Okay, so, but still this will also be accepted. Okay, now, say this is my P, this is my Q, this is R, and T, U, V, S, W, X. Now I can have previous kind of rules. So what I can say, okay. So APQ. Okay, what am I reading? I'm reading a 0 here, and I'm pushing them onto the stack. I'm reading this 1, popping this 0. I'm reading one more 1, popping this 0. Now I'm reading a 1, pushing it onto the stack. I am reading one more 1, pushing it onto the stack. I'm reading a 0, popping this 1. I'm reading another 0, popping this 1. Okay, so that's what is happening. Now, AP, not APQ, APR. So, but if you consider each one of these, this is similar to the previous case. Okay, so can you tell me APR goes to 0, ATU 1, right? Similarly, ATU goes to 0, AVV 1, and finally we can write AVV goes to epsilon, because grammar should terminate, right? So that is the terminating point. Here also similarly we can write ARQ goes to 1 ASW 0. ASW goes to 1 AXX 0 and AXX goes to epsilon. Okay. Now this is fine, but what is the start symbol of this grammar? The entire thing, starting point to the ending point, that is the variable will be APQ. Okay, so APQ will go to or is it going to one of these? Both of them. So how do I write? Yeah, intersection. So for strings, what do you call it? Concatenation. So it is APR ARQ. That is what we are writing as S goes to S1 S2. Okay, so this portion is generated by S1. So you can think of it as S1 generates. So basically what is happening here? So this is sort of broken down into two parts. This is generated by S1, this is generated by S2, and this entire thing is generated by S. Okay, so S1 derives 0, 0, 1, 1 in 0 or more steps, and S2 derives 1, 1, 0, 0 in 0 or more steps, and finally S derives this entire thing 0, 0, 1, 1, 1, 1, 0, 0 in 0 or more steps. Okay, so that is the mapping. So now let's write explicitly the variable mapping and rules mapping. So my start variable is S, and here start variable is APQ, and S1 is APR, S2 is ARQ. Okay. So rules, S goes to S1 S2 maps to APQ goes to APR ARQ, and S1 goes to 0 S1 1 maps to APR goes to 0 ATU1. In this case we write like that, but like I said, technically PR and TU are relative terms. TU currently can become PR later. Okay, so just keep that in mind. And similarly S2 goes to 1 S2 0. Here ARQ maps to 1 A SW 0. Okay, so that is how we are sort of constructing the grammar from the PDA. Okay, so this grammar is purely constructed out of PDA. I am only comparing with the grammar which we built independently, just for you to understand that this is a proper grammar. Okay, yeah, so let's proceed. Okay, so this is how it is done. So right now I just showed you an example. Now we will move on to the general proof of the theorem, how to prove it in general, how to convert any PDA to CFG. Okay, so two-step proof. First, you need to simplify the PDA. Second, you need to build the CFG from the simplified PDA. Now this first step again has three subparts. First one, how do you simplify PDA? Three steps you simplify the PDA. First, you should modify the PDA such that it has only one accept state. Second, the stack should be empty before accepting. So even if some symbols are left in the stack, you should pop them before you move to the accept state. Third, each transition should have exactly one action on the stack. That is only push or pop, not more, not less. That is, you may have some transitions where both push and pop are there. No, you should convert it to maybe one transition or two transitions or multiple transitions with only one push and one pop. Similarly, you may have some transitions where neither push nor pop are there. Again, you need to convert them to one push, one pop transitions. Okay, so let's look at them one by one. So first case, only one accept state. Okay, before this, let me explain what I'm saying here. So suppose if I have a transition like this, we know this is pop and this is push. So we will break it into two transitions where the first transition A is read and B is popped, and in the next transition nothing is pushed, nothing is popped and C is pushed. Okay, so you break that one transition into two transitions where each of these transitions has only push or pop. Okay, yeah, so only one accept state, straightforward. Suppose you have multiple accept states, you convert it such that you will have only one accept state and you will have epsilon transitions from each of these accept states. So just epsilon transitions. Okay, then empty the stack before accepting. So first, what do we do? Create a new start state. Q naught, which pushes dollar onto the stack. So that it can be popped in the last step to make sure the stack is empty. I don't know if you noticed, you see the nature of PDA is such that whichever symbol is first pushed onto the stack, that is the symbol to be last popped out from the stack, right? Like for instance, if you notice here, you are reading a 0, you first push this 0 onto the stack, then this 0 onto the stack. And when you are reading a 1, you first pop this 0, and then for the second one, you are popping this 0. Okay, so whichever symbol is being first pushed onto the stack, that symbol is the last one to be popped out of the stack. You anyway know that's what stack is. All right, so that is the relation between P and Q. Otherwise, how will the computer know what is the relation between P and Q? Right now, through diagram, you know that P and Q are related because they are at the same level. But I can't specify this to the computer. Okay, P and Q are at same level. It doesn't know. All right. The only way it knows is whatever symbol you are pushing at the beginning, that symbol when you are popping at the end, these two states are related. That's how it relates both the states. Okay, so that is something to keep in mind. All right, suppose I have some state, some start state with some transition arrows. I will add a new start state such that I just push dollar onto the stack. I mean, we already normally when we are building PDA, like I said, the first transition is anyway pushing dollar. In case you're already doing that, then you need not again specially do this. But if you start the PDA without pushing the dollar, then you need to do this. You need to add this state and necessarily push the dollar. Okay. So push dollar in the first step. And finally, you may have some state. So before the accept state, we pop all the remaining symbols from the stack. So if you have some X on the stack, all X's, you pop from the stack for all X belonging to gamma minus dollar. So except dollar, you push all the remaining symbols in this step, and final step you pop dollar. Okay, so pop dollar in the last step. Okay, and then no, it's like this is mostly for those cases where you need to skip the symbols. It's like, you see, these are all accept states, right? And then you are creating another accept state, or this is an accept state and then you are creating another accept state. Okay, so it's like excess symbols in the stack. You know the string will be accepted. Like you remember a power I, b power j, c power k, where if the number of a's and number of b's are equal, then c's you don't worry, you just skip them. Or if there are additional symbols in the stack, you know you have nothing to do with them. You know the string has matched, you just skip them, you just pop them like that. Okay, make sure each transition pushes or pops but does not do both or none. So if there are two states, say P and Q, with a transition like A, B goes to C. So you modify it such that between P and Q, you add one more state, or in the first transition, you read A, you pop B, you don't push C. In the second transition, you read nothing, you pop nothing, you push C. Okay? Then let me copy this. Now, what about the other case where you don't have anything, neither push nor pop? That case also you should cover, right? You need to modify that case also. So what if both B and C are epsilon? That should also be modified such that you have one push and one pop. So initially, you don't pop anything, you push a dummy variable called ZD, and then you pop this dummy variable. Okay. So in the previous case, you're only popping because those are not dummy variables. You already have B on top. You pop it. And in the next transition, you push C. Now in this case, we have nothing to push or pop, but we have to push something, pop something. So I push a dummy variable and then pop it. Okay. Not variable, sorry, ZD is not a variable, it's a dummy symbol. What about A? Should A be epsilon? Should A not be epsilon? Nothing like that. A may be epsilon, A may not be epsilon. There is no restriction on A. Okay, so it is allowed. If it happens, it happens, otherwise no. Okay, so now we are done with simplifying the PDA in 3 steps, right? So what did I say? The first step of the proof of the theorem is to simplify the PDA. This itself has 3 steps. So that's what we saw so far. Now the second step is to build the CFG. Okay, so we saw the 3 steps in detail. Now we need to build the CFG from the simplified PDA. Okay. So given the PDA, at the end of step 1, in a simplified form, we build the CFG with the following rules. The first one is, for all P belonging to Q, add a CFG rule APP goes to epsilon. Okay. Then for all PQR belonging to Q, add a CFG rule APQ goes to APR ARQ. Okay. Then for all PQRS belonging to Q, add a CFG rule APQ goes to ARS B if 2 conditions are satisfied. The first condition is delta PA epsilon equal to RX, and the second condition is delta SBX equal to Q epsilon. But technically speaking, these rules need to be modified like this, that is, Rx belongs to delta PA epsilon and Q epsilon belongs to delta SBX. So let me explain. It's actually easy. So if you remember, what did I say? If you have a scenario like this, suppose this is my P, this is my Q, and this is my R, this is my S. Now on reading A, I am going to R, and the stack is changed to a state where there are some symbols and I pushed X onto the stack. Okay, so this may be here also, something may be here also, even before this. But if we are starting from this state and say in this state up to this state, say there are whatever symbols are there, say this is my T. Okay. And now I'm pushing an X. I'm reading A and I'm reading some symbols and I'm reading a B. When I'm reading A, I'm pushing X onto the stack and I am going from state P to state R. So in state P, I have only symbols up to T. In state R, I have T and an X. Okay. Now, again, after that, I'm pushing something, I'm popping something. By the time I come here, again, I come to this state where I have X on top. Now, I am reading a B and I am popping this X and I'm going back to state T, which means I'm going back to state Q. Okay. This is the scenario. Now, this is represented like this. So here we say APQ goes to ARS B. That's what we wrote earlier, right? APQ goes to this small a. This is my ARS, right? ARS B. Okay. So that is what is being mentioned here. So here, when I'm in state P, if I read a symbol A, I push X onto the stack and I go to state R, right? So if I'm in state P, I go to state R. When if I read a symbol A, I go to state R, but at the same time, I am pushing symbol X onto the stack. Now the same symbol X, I am popping when I'm in state S. I am popping this same symbol X when I am reading B. I am popping this symbol X and I am going to Q. Now, how do we specify this? Delta PA epsilon equal to Rx, right? Delta PA epsilon equal to Rx. You push X, you go to state R. Similarly, here what do we do? Delta SBX equal to Q epsilon. Delta SBX equal to Q epsilon, right? But technically, these are the states we know. There may be other states, output pairs, we don't know. So we should not write equal to. We should say that particular tuple belongs to this output. So this thing should be modified like this. Rx belongs to the output delta PA epsilon. Similarly, Q epsilon belongs to the output delta SBX. So that is what is written here. Okay. So whatever I showed in diagram, that is being written as a second rule. This one. This one. This is quite straightforward. No, if you look at the diagram, this PQ is the entire thing, but that is formed out of what? PR and RQ. Okay. Or I was about to explain that in the next one. Suppose if I have, in the previous case, we had only 2 ups and downs. Suppose if I have 3. Okay. Now let's say this is my PQ and this is my RS. Now PQ can be thought of as APR concatenated with ARQ, or it can also be thought of as APS concatenated with ASQ, or it can also be thought of as APR, ARS, ARQ, ASQ. Right? That's it. So every possibility you take, whatever is in between, you take all possible concatenations. That is what is saying. This one, this one, what is the doubt? No, this is not related to this rule. This is related to this rule. Third rule, not the second rule. Okay. So now, so whatever rules we saw in the previous page, we will give the visual representation of those rules here. So for every P, you add a rule, APP goes to epsilon. And for three states P, R, and Q, you add a rule, APQ goes to APR, ARQ. So here, what does this mean? This means R need not be, I mean, these three states need not be immediate consecutive states. There can be an indirect path between P and R and indirect path between R and Q. And you can still add this rule. Like I showed, APRSQ. In that case, you can also think of PS and SQ or PR and RQ. Okay. So, and it's also not necessary that these three states are mutually exclusive. Sometimes if you have a self loop, then all these three are same. P, R, Q are all same. We'll see an example in a while. And now suppose you have four states. P, R, and you're going from P to R on reading A, and you're pushing X onto the stack. Now, there may be many states in between, and you're going to S, and finally on reading a B, you're popping this X from the stack, and you're going to Q. Okay. Now in this state, if this is the scenario, you add the rule APQ goes to ARS, B. Yes. Yes. I didn't get the question. Yeah, this will be the topmost. What I'm saying is, in this step, you're pushing X. So that will be the topmost. After some steps, this X will come on top. Yes. It's not like you are designing. That is the process. That will, you see, when you are pushing something, again for the stack to be empty, whatever you pushed, at some point it has to be popped, right? So at some point it has to come on top. That is this point. That's what I'm saying. And A equal to epsilon or B equal to epsilon are allowed. Okay. And what will be the start variable? From the PDA, how do we derive the start variable? Nothing. Take the start state and the accept state, and whichever variable has them as subscripts, that is the start variable. Or you can say APQ if P is the start state and Q is the accept state of the PDA. Okay. All right, now let's look at an example. So let's build the PDA for the language where each string has equal number of zeros and ones. Now you should imagine that you don't know the grammar. You're directly building the PDA. You're given the language, you're building the PDA. Now you try to convert this PDA to the grammar. Okay, now you get a grammar from the PDA. Now through some independent route, if you can build the grammar of that language, you can compare both. Through this method, whatever grammar I got and independently whatever grammar I built, are they same or not? So that's what you should do. Okay, so basically it's a simple PDA. You start with Q0, and you push dollar onto the stack. You go to Q1. Now the entire computation happens here in self loop. That is, if you are reading a 0, if 1 is on top of the stack, pop it. If you are reading a 0, if 1 is not on top of the stack, push this 0 onto the stack. If you are reading a 1, if you see a 0 on top of the stack, pop it. If you are seeing a 1, if 0 is not on top of the stack, just push this 1 onto the stack. Okay, that's it. These are the only 4 cases we saw. Those 4 cases we specified here as transition labels. And finally, you pop this dollar from the stack and you go to the accept state Q2. Okay, now fortunately, this PDA is already in the simplified form. You need not simplify it further. Sometimes PDA may not be in simplified form, then you need to simplify it. Okay. In this case, it is in simplified form, so we can directly start building the CFG from this. So what do we do? So first, let's try to write the rules, or let's try to write the variables. What all variables you will get from this PDA? You will have, so instead of writing a q0 q1 like that, I'll write a01 00 like that. So a00, a11, a22, a01, a02, a12. These are the variables. Now what are the rules? First, for every state you add a rule like app goes to epsilon. So you add rules like a00 goes to epsilon, a11 goes to epsilon, a22 goes to epsilon. Now add the second kind of rules, that is apq goes to apr arq. So here you can think this is p, this is q. So a02 goes to a01, a12, right? But I said PRQ need not be necessarily mutually exclusive. In this case, there is a self loop. So this thing itself can be P, this itself can be R, this thing itself can be Q also. Okay, we'll come to that. But these two themselves also can be PRQ. In this case, this is my P and this is my R and Q. And these two things can also be my PRQ. In this case, this is my P and R, this will be my Q. Okay, so first let's take this case, Q0, Q1 case. So A01 goes to A01, A11. And A12 goes to A11, A12. Okay. Now this third case is, this is my PRQ. So here A11 goes to A11, A11. All right. And then now the third kind of rules. This APQ goes to AARSB. Just 5 minutes. Now APQ. So let's take this one. Initially from Q0 to Q1 when I'm going, I'm reading epsilon, I'm pushing dollar. Now the same dollar I'm popping when I'm going from Q1 to Q2 on reading epsilon. Okay. So A02 goes to, what are you reading? Epsilon. You are pushing dollar, popping dollar, that will not come in the rule. Whatever you are reading, only that will come in the rule. You are reading epsilon and pushing dollar. Okay. And you are going through A11 and then you are reading epsilon and popping the same dollar and going to 2. That's it. You started with 0. You read epsilon, you pushed dollar. Okay. Then you read some things in between. Then you read epsilon and you popped dollar and you came to 2. Okay. And now again in A11, you are reading a 0 and you are pushing 0. Now the same 0 you are popping when you are reading a 1 and you are coming back to the same state. Okay. So you are reading a 0 and you are coming back to the same state and you are popping this 0 after reading a 1. Okay. Similarly, you are reading a 1 and you are pushing 1. So you are reading a 1 and you are pushing 1. Now this 1, when are you popping? When you are reading a 0. Okay, so on reading 1 you are pushing 1. On reading 0 you are popping the same 1. In between which states are you visiting? You are in the same state, A11. Okay, that's it. All the rules are done. Now let's see whether it is mapping to the grammar we know or not. The grammar we know will take the simple form: S goes to 0S1 or 1S0 or SS or epsilon. Okay, now let's look at the rules. S goes to 0S1. Which rule maps to that? This one, right? S goes to 0S1. S goes to 1S0. This one maps to that. S goes to 1S0. S goes to SS. Which one maps? This one maps to that. S goes to SS. Okay, S goes to epsilon. Which one maps? This one. S goes to epsilon. Okay, so if we look at variable mapping, what does S map to? A11, right? But the start variable is not A11. Here the start variable is what? In this PDA, what is the start variable? A02, right? But A02 is not mapping to S. A11 is mapping to S. So what to do? But it's not a big problem because A02 is just like an additional start variable. So I can modify my grammar saying S0 goes to S. This is not really fundamentally changing my grammar. So I will say S0 equal to A02. Then this will map to, where is A02? Yeah, so this will map to the rule S0 goes to S. Or let me write it here. S0 goes to S. Okay, now these rules are redundant. They are unnecessary because they are not reachable from the start state. They're not reachable from the start variable. You see, A00, is it coming anywhere on the RHS of any rule? No. A22 is not coming in the RHS of any rule. A02 is not coming in the RHS of any rule, and so on. So it is like in DFA there are some unreachable states. Similarly, these are unreachable variables. So you can ignore them. All the rules which you know of the grammar, which you built independently, all those rules are also present in this grammar which you derived from the PDA. So this is a proper grammar. Yeah. This one? Yes. A11, A12, thanks. Yes. Yeah. Yeah, A00 goes to epsilon I crossed because what is the start variable? A02, not A00. From A02, are you able to reach A00? No, because A00 is not present in the RHS of any rule. If it is not present in RHS of some rule, how can you reach it? If A02, somewhere here A00 should come. There is no rule where A00 is coming in the RHS. So you can never reach that from the start variable. So there is no need of those rules. Okay. So that is the second part of the theorem. That is the proof for the second part of the theorem. So we are done with second chapter. Actually, there is also pumping lemma for CFLs. We'll not look at that this time. We don't have time for that. So we will close second chapter here. So whatever we covered so far in second chapter, that is part of your syllabus. And whatever we cover in the remaining lectures. But for the quiz, whatever we covered until today, that is part of the syllabus. You will have quiz on Saturday. Okay? Fine. So let's stop here. And I'll upload all the lecture notes and whatever videos I have by tonight.